Welcome to our newest project. We will go a bit further back in time to the previous millennium. 25 years exactly to the year 1998 and the best machine that we could assemble from that year. Not gonna lie, this one made us nostalgic as hell, and we weren't even PC players in the Pentium II era. So let's see how well we'll build it and how much fun is there to be had with a 1998 high-end gaming PC. As we usually do, we'll start with our motherboard. Chaintech CT-6BTA3 is a nice board for this build. At the time incredible Intel 440BX chipset was the envy around the block. 4 memory slots are a positive surprise, as most motherboards back then had 2 or 3 slots. Its slot 1 supports all of the Pentium II CPUs, and with the corresponding BIOS upgrades, some of the Pentium III ones as well. One of the new features at the time was an AGP slot, supporting all of the 3.3V AGP cards. This motherboard works beautifully, as its stability and feature-rich support made us forget for a few moments how old this system is. As good as it is, it wasn't our first choice. We only got our hands on it after our first choice had a cap explosion and 98% progress of installing Windows 98. In the coveted slot 1, yes, CPUs were going into the slot at that point in time, we'll place the best CPU there was in the year 1998, which is Pentium II 450MHz from the Deschutes generation. On the card, the processor was accompanied by 512KB of L2 cache. The cache separated, but this close to the CPU was the reason why chips were placed on the cards in the first place. It also had MMX support right out of the gate, as it was an improved version of the Pentium Pro chip. Its clock was made by a 100MHz FSB and a clock multiplier of 4.5. The TDP of this beast is a mere 27.1 watt. As soon as we got it, we knew we wanted to make a build around it, and made it we did. With 4 SDR memory slots, with the largest supported sticks being 128MB, we can go up to a whopping 512MB of 100MHz SDR memory. SDR memory sticks were a compatibility nightmare, and it took us a while until we got 4 of them working. And still, one of them was secretly faulty or incompatible. The final ones we got working don't make any sense at all, but the mojo around it seems to be fine. For storage, we are using 16GB compact flash cards via IDE to compact flash adapter. We found them the most convenient, and they are the de facto standard in the retro community, so we found a lot of support for this approach online. For something more era specific, we have this IBM 4.5GB HDD. The problem is we don't know if it works at all, and we currently don't have a functional SCSI controller, and this is a SCSI disk. For the power supply, we've used multiple different ones without any problems. Besides that cap popping, that one was caused by a motherboard issue. If we were choosing graphics card in 1998 with an unlimited budget, we would most likely get 2 of the 3DFX Voodoo 2 cards. Those cards were used together with Scanline Interleave technology, or SLI for short. The idea is to have each card render every second line of the frame, thus theoretically doubling the performance. But the budgets are limited even today, and these cards are almost as expensive as they were back in the day. The good thing is that we have a foresight on what would be a better purchase in retrospect. And our alternative comes from the underdog company named nVidia, in the form of a Riva TNT card. While some may say that the TNT in the name tells you a thing or two about card overheating, it's actually short for Twin Texel. Cringe-inducing short for sure, but that's what it is. This AGP version sports 60MB of VRAM, is clocked at 95MHz and supports DirectX 6 and OpenGL 1.5. But similarly to our motherboard, it wasn't our first choice. We started with this 16MB VRAM PCI Riva TNT card from STB Systems, but as soon as we started working on this project, we realized it was actually faulty. When we booted into the OS, Windows 98 in this case, we got a bunch of vertical lines on our screen. Installing drivers made us have a long-awaited rendezvous with our old blue friend. So we realized that this one is sadly out of the picture. Not to be dismayed, we ordered the TNT card we already showed you. In the meantime, we played around by using a different card from 98, Matrox Millennium G200. This card has a memory upgrade card in the predefined slot, for a total of 16MB of memory. The cleverly assembled heatsink doesn't seem to be there from the factory, but works nonetheless. As you'll see, we initially assembled the system with this card, and you'll see its results in the benchmark charts as well. Here is the list of parts we used in this PC build. With everything assembled and our machine working, now it's time to benchmark and observe the results. We'll start with the granddaddy of FPS games, Doom from 1993. Here, different graphics cards don't make any difference. This game is software rendered, which means that all the work is done by the CPU. With 100 plus FPS in every preset, this game is perfectly playable in every single variation of settings. This is interesting considering that this game barely broke 20 FPS on the new machine from a few years prior. Next is another masterpiece from id Games, Quake from 1996. To play it properly, you needed at least Pentium I. But Pentium II here knocks it out of the park, with 30 plus FPS on 800 by 600 resolution. This was an amazing performance back in the day and shows how fast technology was progressing in those years. You may notice that we were until now only running id Games as benchmarks, and that's for multiple reasons. One is that those games are the best looking games of the era, and another is that they have built-in benchmarks. We've also tested this machine with the 1997 game Blood from Monolith Productions, and the First Age of Empires game, also from 97. We couldn't gauge the exact performance of these games, but we can confirm that they work beautifully on our 98 system. Continuing with id Games games, let's see how well our PC stands its ground in Quake 2. This one is interesting considering this one has both software rendering and integrations with multiple graphics APIs. What are those APIs and why do they matter? Why do some graphics cards perform better in some games than others, which in turn perform better in other games? Let's try answering those questions. Graphics API is a toolkit for game code to communicate with graphics hardware. Think about it as a standardized interface to send points in space. How those points make up a polygon, textures, and code to determine which exactly is that point going to show up, and code to determine which color each pixel is going to be, optionally using textures that you've sent beforehand. Here we're going to list the APIs in use today. DirectX, currently at version 12, proprietary API from Microsoft that has been the de facto standard for 20-something years. Vulkan, open source standard, successor to OpenGL that's the strongest contender to DirectX. An example of performance you can get by using it can be seen in the new Doom games. OpenGL, latest version 4.6, deprecated by Vulkan but is still in use, as it's simpler than its contemporary counterparts. Metal, a proprietary API from Apple, which exists. God knows why. And here are the APIs you had in play back in 1998. DirectX at version 6.0, Windows 98 exclusive, supported by Matrox and nVidia cards. OpenGL at version 1.2, supported by, again, Matrox and nVidia, and 3dfx by using mini-GL layer. Glide, proprietary API used only by 3dfx Voodoo cards. Quake 2 supports OpenGL and Glide, so we'll use OpenGL for both nVidia and Matrox cards. We'll also see how it performs via software rendering. nVidia card seems to create more overhead for CPU than Matrox card, and as such, easily beats G200 on high details and resolution, and is beaten heavily on low. Both cards beat software rendering, which is expected, but TNT loses on the low details, most likely due to overhead we mentioned. Either way, on all variants, except maybe on one we called very high, this was considered a playable experience for Quake 2. How about we give a little competition to id Games here, in the form of the first Unreal game from 1998. Epic Games' debut supports DirectX, so we'll see how our cards fare using this API. With excellent support for DirectX, Matrox G200 holds the line in this game, but is still beaten by nVidia TNT in all presets. The game is playable on what we set as low and medium preset, and playing it on high is a bit of a acquired taste. Returning to id for our next game, the TNT card shows how brightly it shines in Quake 3 Arena. While sporting similar results to the Matrox card on low preset, it decimates G200 on the higher ones, doubling or tripling the performance. With the G200 we get playable experience on the low preset, while with TNT we get playable experience on all the presets. In Grand Theft Auto 3 from 2001, we get similar unplayable experience from both of the cards. This may be due to both the graphics card and CPU not being powerful enough to run this game. We find TNT's performance here a bit suspicious, as we expected better and we suspect drivers to be the culprit. Anyway, we couldn't manage to find better performing drivers, so we'll just go with these numbers. 4 years later, in 2002, we noticed that our PC aged quite rapidly. The CPU we got is the most powerful Pentium II that ever existed. With BIOS update we could upgrade to some slot 1 Coppermine Pentium 3, or maybe some socket 370, who knows? But first, we want to see how far this CPU and motherboard go, and with memory already maxed out, a graphics card upgrade is our only choice. And yet, there, we are limited by our AGP slot. It supports only 3.3 volt cards, and all newer ones work on 0.8 or 1.5 volt. You can differentiate which card supports which voltage by looking at the notches on their socket insert. If it has a notch nearer to the backplate, it's a 3.3 volt one. If it's further, it's a 1.5 or 0.8 volt one. If it has both, it can work both ways. The best card that supports both voltages that we have is GeForce TI 4200, the same card we used in our 2002 high-end. But don't let 2 in its name drive you to the wrong conclusions. This is in no way a low-end card. Its naming certainly didn't do it any favors, as this card was an excellent performer at an affordable price. In Quake 2 we maxed out performance on all the presets, so much that we hit the FPS limit on all of them. Not sure if it's the CPU bottleneck, the GPU driver overhead, or what went wrong, but we got a slightly worse performance in Unreal. With consistent performance on all of the presets, we can confidently say that we reached our CPU limits in Quake 3 Arena. In GTA 3, we got that semi-masochistic playable experience. Once again, we suspect that CPU is holding us back. Morrowind, oh Morrowind, for what thou pain you cause us, with thou not optimized and thou we cry. The only thing more cringe than the previous sentence was our system's performance in this game. Next, we tested the very first Call of Duty game from 2003. It's made using an improved Quake 3 engine. And similarly, the game performance we got was excellent and playable on all the presets. On our machine, Far Cry was barely running on low preset and failed to run on the higher ones. Compared to our 2002 high-end machine with the same GPU, we can safely say we hit our 1998 machine's limits. Here are the results of the synthetic benchmarks that we ran. Today, it is much easier to set expectations of PC performance based on the hardware provided. If you have a decent enough CPU that doesn't bottleneck the graphics card much, your game performance will be somewhere in the ballpark of the aforementioned graphics card. Unless you try to play Starfield or some other CPU-dependent game of today. The idea behind modern graphics APIs is to offload as much work as possible to the graphics card as painlessly as possible. That includes loading ideally all of the necessary assets to the VRAM. Even some non-graphics related tasks are running on the GPU. AI, for example, as its architecture provides much better process parallelization. Back then, CPUs were a much more important variable in the performance equation, and you can get quite limited by them. This PC, however marvelous at the time, aged quite quickly, as PC performance year by year was skyrocketing back then. Moore's Law in '98 was at its best and saw our Pentium II clocks almost doubled in the very next year, which made it deprecated fast. Of course, as we mentioned already, we can try using the Slocket to cram in a much more powerful Pentium III chip. But that is a fun project for another day. We sure did have fun with this one, and we will eventually go even further back in time. See you on our next time travel.